Okay, no advanced use from the result of what is computed from MIRtoolbox. Maybe you want to get the actual MATLAB format of the data, so using MIRgetData. So let's say you have a very simple analysis of one file, compute the spectrum. Then, in this case, MIRgetData will return that vector. If it's frame decomposed, what will be written is a matrix. Each frame is one column. If it's a filter bank decomposition, then we use the third dimension of the matrix for the different channel. Now it gets a little more complex. Let's say it was already segmented, so the spectrum of a segmented signal. Then the MIRgetData will return a cell array because each matrix has a different size. And now if you have a folder of file, so it's the same but for each different file. So you have a cell array on each cell is one file, and then a cell array on each cell here is one matrix. That's why there is this MIRgetData that will try to make the result as simple as possible. And for instance, if you have a picking, MIRgetData can return two outputs, the peak positions and the peak values. And then the get method can return any field of the data of the result. So for instance, the name of the ordinates, ordinates, the samples in the abscissa, the data in the ordinates, the units, and so on, frame position, sampling. And for instance, if you compute spectrum, the result of MIRspectrum, you can, instead of saying the data in the abscissa, you can say also the frequency. And so you can have the list of frequencies, list of magnitude. You can have the phase, as I said previously. And you can also have some flag saying if that spectrum is frequency, mel band, bark band, and so on, if it is power spectrum or not. Now let's speak about memory management. So one problem when you have a big file, important file that take a lot of memory, you can't load the whole file in your computer. And if you try this with in MATLAB usually, then it's a little not responsive, and it's difficult to stop the process because it will use the virtual memory usually. So the idea is that the file will be decomposed into chunks. And so if we wanted to compute the envelope, each envelope for each chunk will be estimated, and then there will be a concatenation. It's possible to do that for MIRenvelope because the envelope extraction is an extensive operation. So you can do that for each chunk separately and then concatenate. Okay, and the good news here is that it's completely automatic. You don't have to care about this. But maybe you have to be careful about the chunk size limitation. So usually these chunks have a maximum size. By default it's 500,000 samples. But if you still have memory overflow problems, then because maybe you have less RAM, you have other program open or so on, you can decrease that MIRchunklim. And for instance, say MIRchunklim 50,000, and this parameter is stored in the memory in MATLAB for this whole session. So now to take benefit of this memory management processes, there are some rules that I need to follow. Avoid useless call to, for instance, MIRaudio. For instance, you want to compute MFCC of a file. If you first say MIRaudio of your file, then it will try to do that. So it will try to return that audio file, and it can't. But if you now say MIRMFCC directly of the file, without first calling mir audio. Then it will do what we wanted to get in the end, decomposition into chunk and so on. Okay, and it's the same with folder of files. If you ask mir audio folder, it will try to keep all these results in the memory. And same for mir frame. If you want frame decompose MFCC, if you try first mir frame, then you will try to store all the frame decomposition into the memory. Whereas if you use this frame keyword, it will try to make it optimal. Okay, but you can't follow this advice always in all cases, because here, for instance, you can't avoid using audio, mir audio. Why? Because you have used one particular operator of mir audio here. So what should we do now? So at that point, you need to be more advanced user of the toolbox, and you have to know about flowchart design and evaluation. So it's quite simple, actually. It means you will do as usual, but you don't specify a particular file or folder. You say, for the moment, it's just a design. So you use the design keyword. And once you have written the whole series of operation, then you can evaluate. You say mir eval of this design, and then you specify the name of the file. Then, for this particular example, it will do the whole process chunk by chunk. And for instance, here, spectrum and centroid. So it will first compute the spectrum for each chunk, the centroid of each chunk, and then final concatenation. Same for folder of files. Now, still there could be some problem, because if you, for instance, compute a spectrogram like this, you want to get the centroid, and then you want to evaluate in order to get the actual value for your particular folder, and then you want to get the capstrum from the same spectrogram and get the actual values. There will be a problem here. It will work, but there is a problem. Can you guess what is the problem here? So there won't be memory overflow, but one particular problem that could be annoying. So here, problem is that when you call twice mir eval, then each time it will compute a spectrogram, which can be a problem. If you have a much complex flowchart, then each time it will compute, for instance, the onset of the whole file and so on. But hopefully there has been a solution for that. You will design a complex flowchart. For instance, let's call it myflow. So it's like a structured data in MATLAB, so we call mir struct. So you have this temporary data that you don't want to compute several times. So you use a particular field, TMP, where you store all this temporary data as a subfield. Here, in spectrum design frame. And now you say there is a field of this structure sent that will be the centroid of this temporary data, and same for the capstrum. Now you evaluate just once the myflow for the folder, and then it will just compute once the spectrogram and then return the two centroid and capstrum. And then it can be more complex. Here it's a little like in mir features. We can define one field for dynamics and subfield for RMS. Okay. We can define some temporary variable onset detection. Then we can have a new field rhythm, a subfield tempo, based on the onset. And then we can compute another temporary variable based on the first temporary variable, and a new subfield attack time and attack slope. So it's possible to do like this.